Okay, let us summarize what we've seen today. We introduced the concept of a system of n first-order ordinary differential equations. So it can be written in a compact form as a single differential equation with a vector unknown. So then we know that any higher order system or individual differential equation can still be converted to a system of first-order differential equations. So then, if a system is autonomous, then the right-hand side does not depend on t explicitly. Then we have seen linear homogeneous systems with constant coefficients. So in order to solve a linear homogeneous system with constant coefficients, we take the matrix of the system and we compute its eigenvalues and eigenvectors, and then we put them together to form the general solution of the system, right? So this is going to work if all eigenvalues are real and there are n linearly independent eigenvectors. So if the eigenvalues are complex, this actually still works, only it gives us a non-real solution. But if you are comfortable with a complex solution, then it's fine. If you are not, if you want to produce a real valued solution, then it's the next week. So but the trickier case is the case of a non-diagonalizable matrix A, so you can read about it in the textbook. So for systems of two equations, we can plot phase portraits on a computer, or we can sketch phase portraits. And there are three essentially different types of the critical point at the origin that we have seen today: nodal source, saddle point, and nodal sink. They are actually very similar to what you saw in calculus 3, to a point of local minimum, a saddle point, and a point of local maximum. So hence, even one word is the same. It's still a saddle point. Then to distinguish between these types, you need to apply a very, very similar type of analysis as what you did in calculus 3. But then to sketch the phase portrait is trickier, but it's not too hard. So we can compute eigenvalues and eigenvectors, and then we can sketch the phase portrait. Well, and finally, I would like to clarify a little bit more about the general theory of linear systems of differential equations, right? So that's the most general linear system in a matrix form. And then we have the theorem of existence and uniqueness of solutions, right? So if the right-hand side of the matrix, so if both p of t and g of t are defined on some interval from alpha to beta, then the initial value problem has a unique solution on the same interval from alpha to beta. This is for linear systems. If the system is non-linear, then still we have the theorem of existence and uniqueness of solutions, but the domain of a solution can be smaller than the interval alpha from alpha to beta. So if we have a homogeneous system of linear differential equations with n equations and n unknowns, then the dimension of the solution space is n. So if we have a non-homogeneous system, then every solution of a non-homogeneous system can be expressed as a particular solution of the non-homogeneous system plus the general solution of the corresponding homogeneous system. So, and then if we have n vector functions, each of them is a function from R to Rn. So let me write it so that xi is a function from R to Rn, right? So the dimension of the vector is the same as the number of functions. And by putting all them together, so that's the first column of the matrix, that's the second column, and so on, that's the last column of the matrix, we can form a huge matrix, and its determinant is called the Wronskian. And just pretty much like for individual second order differential equations, the Wronskian is 0 if and only if they are linearly dependent. Well, I mean, if these are solutions of a system of differential equations. Okay. So there is also an analog of Abel's formula, and there is even a method of variation of parameters, but of course it becomes pretty complicated when you apply it to systems, but it still exists, which is why you know, when we have a system of differential equations that goes like x prime equals p of t times, sorry, say a constant matrix times x plus say g of t, then changing g of t with a constant vector doesn't make it simpler, because there is variation of parameters anyway. Okay, so which is why the kind of the easy case when the matrix is constant, but the free term doesn't matter whether it is constant or not. Okay, so that's all for today.